Welcome, everyone. Today we're diving into some genuinely fascinating research from the IIETA. That's the International Information and Engineering Technology Association. We're going to decode the digital sleight of hand that actually powers those modern virtual worlds we all love exploring. If you've ever stopped to just marvel at how gorgeous a modern 3D environment looks, you've literally witnessed the exact battle we're covering in today's explainer.
It's a completely relatable question, right? Why do realistic shadows constantly threaten to melt our graphics cards and basically turn our rooms into saunas? Well, creating beautiful, physically accurate lighting in real time is frankly an absolute computational nightmare. Rendering the intense physics of light, bouncing and blocking in 3D space is easily one of the heaviest burdens you can place on a system's hardware.
Okay, let's dive into this. We're keeping it moving today, covering, first, the quest for realistic shadows. Second, the high cost of softness. Third, dividing the view frustum. Fourth, smart filtering in textures. And finally, proof in the performance. Starting with part 1, the quest for realistic shadows. This really is the holy grail of light.
Lighting is basically the ultimate holy grail in digital rendering and global illumination. And the difference? It really comes down to hard versus soft shadows. Hard shadows are created by single-point light sources. They've got these incredibly sharp edges and, let's be honest here, they just look artificial and fake in a 3D environment. Soft shadows, on the other hand, are cast by area light sources. They give you those beautiful, natural gradients, what we call the penumbra, and they look visually authentic. Think about it. When you're walking under a street lamp in an open-world game, the way the shadow blurs at the edges the further it gets from your character, that is exactly what grounds you in that reality.
So, what does this all mean? The researchers summarized it perfectly, stating, "A crucial element that sets apart realistic images from counterfeit ones is the inclusion of soft shadows." That quote hits the nail on the head. It shows us exactly what's at stake here. For computer graphics developers aiming for total immersion, achieving this effect isn't just some nice-to-have bonus feature. It's an absolute necessity for authenticity.
Moving on to Section 2. The high cost of softness and the technical bottlenecks standing in our way.
We absolutely know we need soft shadows, but here's where we hit a massive technical bottleneck. Achieving this level of realism is a total nightmare for computing power. To understand why, we have to look at what an area light source actually is. It's a light that spans a physical surface rather than just being a single tiny dot. So, to simulate the physics of an area light mathematically, you actually have to chop it up into dozens of individual point light samples. Then, your hardware has to run a massive visibility test, a rendering pass, for every single one of those pieces just to create that natural penumbra effect we were just talking about.
And this brings us to a frankly staggering number, 256. That is the massive number of shadow maps the mathematical ground truth method requires. Now, the ground truth is essentially the ideal expected outcome that perfectly reflects reality. To get that flawless soft shadow, you have to sample the area light source 256 times, generate a unique shadow map for each one, and then combine the whole shebang. That's 256 unique shadow maps combined for just one single frame. So if you're playing a game at 60 frames per second, your hardware is sweating trying to calculate over 15,000 shadow maps every single second. It's just mathematically exhausting.
Which brings us to Section 3, dividing the view frustum. This is where the magic trick happens.
To get around this massive computational roadblock, researchers proposed a completely innovative algorithm. Let's walk through it quickly. Step 1, partition the frustum. Step 2, take light samples. Step 3, generate shadow maps based on those partitions. And finally, Step 4, filter and display. It sounds pretty straightforward, right? But the true elegance is all in the execution of that very first step.
Now, what's really interesting about this slide is how the camera's view frustum, which is essentially our cone of vision, is split into 3 cascading parts: near, middle, and far. The algorithm basically tricks the human eye by cutting our vision cone into these specific zones based on distance or depth along the z-axis. By partitioning the camera view separately like this, we don't have to treat the entire scene with that same heavy mathematical burden. It's a lifesaver for your GPU.
Let's look at Section 4, Smart Filtering and Textures, and how we manage all that raw data.
To manage everything, the system uses what's called a progressive disclosure of complexity,
Check out the Cascade zones, their resolution, and something called the PCF kernel size. That's basically a filter used to soften shadow edges and get rid of jagged aliasing. In the first Cascade, the near zone, right up close where the player actually looks, we spend our precious computing power on a high-resolution 5x5 kernel. But in the third Cascade, the far zone, way off in the distance, we cheat. We drop it to a low resolution with a 2x2 kernel. The human eye literally doesn't notice the lower quality far away, but let me tell you, your graphics card absolutely notices the saved workload.
To pull this off smoothly, the system uses two extremely clever tools: hardware occlusion queries, or HOQ, and texture arrays. These allow the shader to efficiently juggle up to 512 shadow map textures in a single unified pass. The HOQ is particularly brilliant here. It acts as a smart stop switch. It gauges visibility based on the screen pixel count, and if it determines a shadow is subdivided enough for the human eye to buy it, it just halts the process. It stops unnecessary subdivision instantly, which is absolutely crucial for saving precious frame rates.
And finally, Section 5, Proof in the Performance, the grand finale.
And this brilliantly illustrates the actual results. Looking at this side-by-side visual proof comparing the optimized method with standard approaches, look closely at the shadows cast by the chairs in those trees. The human eye practically cannot tell the difference between this optimized multi-kernel cascaded cheat and the computationally heavy, flawless ground truth physics. The shadows are beautifully soft, authentic, and totally immersive. But here is the ultimate data punchline. When we look at the frame rates, the difference is just staggering. The first bar is the older FSLS method, way behind. The second bar is the SBFS method, clocking in around 325 frames per second. But that third bar, this new Cascaded method, rockets all the way up to 717 frames per second on the test hardware. That is a massive 44 to 51% boost in frame rates compared to the previous leading methods, and it does it all without losing visual fidelity. No way, right?
And hey, if you don't trust your naked eye, trust the math. Comparing the ground truth against our new method using the SSIM value, where a score of 1 means perfectly identical, we see this new method hits incredibly near 1.0. This proves, mathematically, that this optimization doesn't sacrifice a single ounce of physical correctness or visual quality to get those massive frame rate boosts.
So, let's quickly recap the key takeaways of this explainer. This new method successfully achieves real-time soft shadows. It boosts frame rates by up to 51%. It completely eliminates those ugly, jagged aliasing artifacts by using a clever multi-kernel PCF filter based on camera distance. And finally, it's visually indistinguishable from the heavy 256-sample ground truth. Honestly, it's a complete victory in the battle between realism and hardware limits.
So, I want to leave you with this provocative thought. As these brilliant rendering tricks become entirely indistinguishable from real-world physics, but cost half the computing power, what new, massive, and breathtaking virtual worlds will we be able to explore next? The ceiling for real-time computer graphics just got pushed a whole lot higher. Thank you so much for joining me for this explainer today. I hope you found it as fascinating as I did.